webcast continues the discussion of the lab on conservation of momentum. We're currently in part 2, looking at elastic collisions, and we've just finished step 30, which was to fill in the post-collision velocities for each item in the table. So if you've done that, at step 31 it says, okay, let's make a scatter graph of the momentum after the collision versus the momentum before the collision. If you will, if you look at the Excel file that was given to you, it actually creates this graph automatically. It has copied over the system momentum before and after the collision into this table to the right, and it has made this graph. And so we can basically just put this graph in our report here as figure 4. So if you look at this graph, it is linear, right? And it looks like it passes through the origin. Here's the origin. There's a point at the origin, 0, 0. So since it's linear and it passes through the origin, that tells us something about the kind of relationship that we have here. So, so let's say that at step 32, you know, the graph of the post-collision momentum versus the initial pre-collision momentum is linear and passes through the origin. Therefore, the linear momentum after the collision is directly proportional to the linear momentum before the collision. Okay, so we have a directly proportional kind of relationship, and we need to get the slope so that we'll be able to write a physics equation. So to get the slope, I'm just going to do linear regression on this this data. So I'll go to data and data analysis. Go to regression. Let's see, I have a few things. Okay, so I want to first give it the y values, which is the momentum after the collision. And then I give it the x values, which is the momentum before the collision. I want to make sure residual plots and line fit plots are selected, and I'll say OK. Okay, so here's my results. I'm going to go to Home, Format, and Auto Fit the column width so that I can see everything clearly. And it looks like I have good results, a nice line fit plot. Here is my slope, okay, 0.998 it looks like. So this is the summary output for part 2, elastic collisions. Okay, since we're going to have 3 of these in our lab report. Okay, so I'm going to copy this and put it in the report because this is the evidence of how we got our slope. Okay, and now that I have that slope, I remember that the value was 0.998, but let's go think about what the units are. So in that graph, I had momentum on the x-axis and also momentum on the y-axis. So both axes had the same units. And so when I did, or found the slope, which is the change in y over the change in x, I've kilogram meter per second over kilogram meter per second. So in this particular case, it is dimensionless. There are no units here. They canceled. Okay? So then it says, explain the meaning of the slope using a statement that begins for every additional. So if I look at the graph again, the momentum before the collision, if that momentum before the collision increased, the momentum after the collision also increased. So for every additional 1 kilogram meter per second of pre-collision momentum in the system, the post-collision momentum increased by 0.998 kilogram meter per second. Okay. And so if we wanted to write a physics equation, our dependent variable is the momentum after the collision, the final momentum, and that equals our slope, which has no units, times the initial momentum. So if you look at that slope, it's essentially essentially 1. So the slope is essentially 1. 0.998, very close to 1. And so that means that the system momentum is the same both before and after the elastic collision. Therefore, the system's linear momentum is conserved during the elastic collisions. Okay, we had the same amount of momentum after the collision as we did before the collision. Okay, we calculated the kinetic energy of the system both before and after the collision. How did the elastic collision cause the kinetic energy to change? Well, if I look at my table, and let's compare. Here, the collision, or the kinetic energy both before and after. Let me get it so that we can see both. So here, but initially the kinetic energy was 0.3125, and at the end it was 0.3125. Initially it was 0.4375, finally it was 0.4375. In every case, as I walk down this table, the system kinetic energy before the collision seems to match the system kinetic energy after the collision. Okay, so we want to say that the table of data at step 30, because that's where we should have pasted our table. So that's where the evidence is. That table of data shows that the kinetic energy of the system before the collision was the same as the kinetic energy of the system after the collision in every case. Therefore, the elastic collisions resulted in no change in the kinetic energy. Okay, so kinetic energy was conserved during the elastic collisions, right? We had the same amount both before and after the elastic collisions. Okay. So that wraps up part 2.